outlook plan of the talk. Okay. And we have discussed about dark matter, and we have said that matter is in the universe is dominated by cold dark matter. About 80% is dark matter, 20% of that matter is in baryons. And one of the things which we will consider is, although we look at an expanding universe, in the scales that we are looking at, which range from, let's say, a few kiloparsecs to a few, maybe a few gigaparsecs, okay? Newtonian gravity is actually a good enough description for looking at these equations of motion. Okay. So general relativistic effects can only come in at much smaller scales or much larger scales. So what is the n-body problem? Okay. It determines the dynamical evolution of n objects which are interacting only gravitationally. Okay. So you can think of the n-body system to be a globular cluster. You can think of it to be galaxies, okay, in which a globular cluster will just be one part of it. Or you can think of it as being bunch of galaxies, or even on larger scales, you can think of looking at or trying to understand the distribution of galaxies on very large scales. Okay. So that is what we are trying to do. And we have to find a way to solve these equations. And luckily for us, the equations are themselves simple. And but what is not as simple is the fact that one has to solve the Poisson equation in an efficient or a fast manner. Okay. So what is the statement of the problem? The statement of a problem is that you have n points or n objects interacting only gravitationally with masses mi, initial positions and velocities, and one has to determine the trajectories at any later time delta t. So what is given is the initial position and initial velocity, which is denoted as 0. And you have to find out at a later time delta t, which is given as 1. Okay. And once you have this, you find it at a later time 2. Okay. So this is the straightforward problem. And for n is equal to 2, you have the analytical solutions. For n is equal to 3, there are some interesting problems like the Earth, satellite, moon problem, the Pythagorean problem, which I'll not talk about. But for n is greater than 2, generally you don't have any numerical solutions. Okay. So how do you go about solving this? So the simplest way to do it is the Taylor expand, okay, to second order. If you want, you can expand to first order. There might be problems there, but we'll expand to second order. So R1 at a later time is the initial position, initial velocity times delta t, initial acceleration times delta t square by 2. Now the initial acceleration is given by the initial position, and it's all the forces that are which determine the acceleration. And similarly, the velocity 1 is determined at a later time, starting from initial position, initial acceleration, and this is the change in acceleration, which we call the jerk term. But I can do a straightforward derivative of this, and it is the acceleration at time 1, which is positions at time 1, which we have found, minus acceleration at time 0 and delta t. So this is the jerk time. So this is straightforward, and one can go about and integrate. And as you can see, these two equations are order n. The part where accelerations are involved is order n squared because you have to compute forces. Now you can change this set of equations into the following set of equations, and you will see that the position at time step 1 is the position at time step 2 and velocity at time step half. Similarly, the half time step is minus 1, which is minus half time step, and A is again position at time 0. So then it becomes this. So this is actually manifestly time symmetric, and you can actually show that this set of equations, which is the second order equation, is equivalent to this set of equations, which means that a second order equation is time symmetric and it is energy conserving. Okay. Now, of course, if you have n systems, you want to do this, you have to compute n square forces because these are pairwise forces, and that is where the problems occur. You can do this numerically if you are working on a small n system, but it becomes very computationally intensive or time consuming if you go to large n systems. So what are the pros of a direct summation method? It is easy to implement. The integrator is time symmetric. You can look at the accuracy, and accuracy is something which is important for, let's say, globular clusters, which are collisional systems. But all of this breaks down when you even look at million particles. And generally, one cannot study large-scale structure with a direct summation approach. Okay, so one way out is rewrite these equations, which is called regularization. But even then, these work for a small n system. Or you buy hardware to speed up these n square calculations, or you buy GPUs again to speed up these calculations. Okay. So we'll next what we'll do is we have looked at just in a static universe the equations of motion. We'll write down the equations of motion in an expanding universe, which will look similar to the equations of motion in a static universe. So you have the equations of motion in physical coordinates to be given by this expression. Then you have a Poisson equation, okay, which is the force equation, and you have to sample the density field by particles in order to start moving particles. Okay. When I rewrite it in co-moving coordinates, it takes the following form. Here x is the co-moving coordinate, r is the physical coordinate, r is equal to ax. So the equations of motion are the same, okay, similar to this. Now you will see the standard equations of motion, which is the Newtonian equations of motion, okay, which is a minus grad phi term, okay. And if I am looking at a static universe, then a dot is 0, so this term drops off, and here a can be absorbed again in phi, it doesn't matter, and you have the standard equations of motion. And then you have something which looks like a Poisson equation. So you have del square phi is proportional to the density contrast. It's no longer proportional to the density, okay, but rather the density contrast. And again, since you're working with particles, you'll have to sample this field by some particles, and you will give certain sizes to these particles, and this is so that the system remains collisionless. And you have to work again. You have to again work with a of t, which is going in here, and that you solve. You find out by solving the Friedmann equations. And in the linear limit, okay, you can find out the solutions. So I've just very quickly written down. You take the Fourier transform. You have something which looks similar to the equations of motion, and the solution of this. These are all time derivatives. One solution is the Hubble parameter. The second solution is given by this. So you have a decaying mode and you have a growing mode. Okay, and the growing mode is what we are looking at. Okay, so now the equations of motion are simple to integrate, but the time-consuming part is solving the Poisson equation, which is basically the force law. Okay, and it scales as order n square because we have to worry about n square pairwise force interactions, force calculations. Okay, so what n-body methods do? Okay, what we'll do is to resort to quicker and more approximate techniques. So although the exact calculation or the pairwise calculation is exact, it's time consuming, but we should be able to come up with a method which is approximate as long, and it will be useful if we can control the errors. Okay. So broadly, there are two methods, okay, to compute interactions, and the third one, which we will discuss, is a combination of these two methods. Okay. The first one is known as a Eulerian method or a particle mesh method, PM. So what you do is you have to solve the force equation or the Poisson equation. So what you do is to solve this in Fourier space. In Fourier space, it becomes an algebraic equation. And once you have phi k, it is rho, you have rho, you have to find out phi. You take the Fourier transform of rho, divide by k square, and you inverse transform, and then you will get the real space, the solution phi, okay, on the grid. And since you're working with Fourier transforms, you're no longer doing n square calculation. This scales as n log n. So if I had million particles, I would have done million square, which is 10 to the 12 operations. But with fast Fourier transforms, I will have to just do it with 10 to the 7 operations or so, okay, which is 5 orders of magnitude scaling or speed up uh, over a direct summation method. Okay, and this is of course assuming that the number of grids is equal to the number of points, particles. So what are the pros of the PM method? It is order n log n. It's extremely fast. It is simple to implement because all you have to do is solve this algebraically, and easy to parallelize with MPI, and periodic boundary conditions, which one has to worry about uh, in our uh, in our boxes, because we have to also look at the amount of power since the box is a representative sample of the universe, one has to worry about power outside the volume we are simulating. Okay, not completely, but we still have to worry about, because uh, the force goes out to infinity. Okay, so we'll assume that these have periodic boundary conditions. Okay. Now, the negative points about this, it has the resolution limit, which is given by the size of the grid. And parallelization, of course, this is no longer an issue, so I should remove this. Okay. And since this has been solved by using pencil FFT. Okay. Now, there are again generalizations to this. So instead, since it was limited by resolution, you do adaptive resolution, and these are adaptive mesh codes which people work with. Now, the next one is Lagrangian or particle-based method, and it uses multiple expansion of the density distribution. So it computes direct forces in real space, and the approximation is that the structure in the entire mass distribution is partitioned into groups nested into larger groups. Okay, and so for example, if I were to compute the force of Andromeda on me, instead of looking at all the particles or the particles which define the Andromeda galaxy, I will just take the mass of the Andromeda galaxy and the location of the Andromeda galaxy, and find out its interaction at my location. So if I were simulating Andromeda with 10 to the 6 particles, I have reduced this calculation to just one operation. Okay, so that is the approximation that I do. That you can, if the object is far away, I can treat it as a single object located at the center of mass of the object with a mass which is the total mass of the object. Okay, so this is known as the monopole term. Okay, you can also look at higher order multipoles, but again, this is generally expensive. It also scales as n log n. It's extremely accurate because accuracy now is in your hand, but it is slower by PM by a factor of 100 or so. It consumes more memory. And if I were to do this on periodic boundary conditions, I need to again add more terms so that I look at modes which are outside, okay, or which are periodically because of the periodic boundary condition, okay, because otherwise I would be neglecting forces outside the volume. Okay, so so if I want, so I have now two methods, both are n log n. One of them is accurate, it is a bit slower. The other one is fast, but it is not accurate. So the remedy is to combine both of them. So what you do is that you keep accuracy at smaller scales, where this is not accurate at small scales, and you keep this to be the dominant part at larger scales, and this is known as 3PM. Okay, so I will not go into the tree method. Okay, you can ask me later. Okay, and I will so so this is what I wanted to say. Okay, so you have the 1 by r square force, okay, which I have plotted here, which is in a log, so it has a slope of -2. So you impose the tree on a short range part of the force, and you do the long range calculation with the PN method. Of course, now the forces have changed. So you have a short range plus a long range, which add up to the total 1 by r square force. Okay. But these have also the advantages, because this now becomes accurate where PM was not accurate, which was at small scales. At large scales, this was taking too much time, so you suppress it. So at large scales, actually PM takes over. Okay, and this is very fast and accurate at large scales. So you get the combination of it being accurate and fast. Okay, and it scales as n log n. And this is actually one of the methods which was proposed by Jasjeet way back, some 20 years back. And it's quite surprising that over the years, this is one of the things which has not changed in the gravity part of the simulation. So people have gone about and done hydro. There are changes to hydro simulations, how they approach hydro. But tree PM is something which is there in most of the largest simulations. So this is like a Moore's law kind of the thing of over the years, what is the computational power? And currently at a large n, or this is mass resolution and the number of particles. Okay, so this is high mass resolution, large number of particles, which are the largest simulations. They are still being run with the tree PM method. And Gadget is something which has been using tree PM for a long time. And most of the big simulations are run actually with Gadget. So how do I go about to run a simulation? I choose my favorite cosmology, power spectrum and the cosmological parameters. Set up initial conditions. This Jasjeet had briefly mentioned in the morning with Gaussian random field, okay, which is sampled from P of K. I have not talked about how to generate velocities, but basically you use the Zeldovich approximation, which relates velocities to delta. Okay, so you take the divergence of this, it will give me something which looks like a velocity, and then you simulate and you analyze. Okay, and once you have particles, so in an n-body method code, what you will get is positions and velocities, and you have to find out halos. Okay, so I'll just briefly discuss what are the halos that we see, or some algorithms to identify halos. So you have a particle distribution, and the first one is called the friends of friends algorithm. Uh, I will say a friend of a particle is a particle such that it is located within a distance which is called the linking length, which is 0.2 times the mean interparticle separation. I will identify all friends of friends for a given particle, and this will be a unique set, okay, which is not overlapping with another group of particles whose that group has been determined with a friends of friends that you can show. And we will define, once I've identified all these friends of friends, okay, so I will have to go, the friends of friends is also a friend, the friend of another friend is also a friend, and I will stop when I stop having friends, okay, or nearest neighbors. And we will define this as a group of particles, which we will call it as a halo. The halo has a center of mass, which is the center of mass of this group of particles, and the mass is the total mass of these particles. So that is one way to identify particles which are bunched or grouped together. Okay, and the second one which one often uses is known as the spherical overdensity method, or the spherical overdensity halos. You identify density peaks or potential minima. What you next do, once you've identified these local potential density peaks and potential minima, you go out in radius, which you call R200, and this is determined such that the density contrast within that radius is around 200 times rho critical around the density peak. And that will tell us the location. The location is the potential or density maxima, potential minima, and the radius is the radius of the halo. The mass within that is such that m by the volume, which is the sphere, is is rho, and rho is around 200 times the critical density. Okay. Now, based on so there is some dimensional problem here. Okay. Based on so you can work with these definitions of halo masses, and this is something which one routinely uses. So I will stop here, and if you have questions, I can take.
So can I ask?
Yeah.
Yes, sorry if this was mentioned. I think there was a power outage during the talk, so maybe I just missed this. So I guess how do you code in the properties of dark matter, and where does the simulation change if dark matter is cold, hot, or interacting? Maybe you can just briefly summarize.
So one part which you can put in is the power spectrum. So often one changes the power spectrum. So if you say it is warm, then you will truncate the power spectrum in some manner at small scale.
So you don't really put in like at least the definition of cold dark matter. It decouples at non-relativistic velocity. So you don't put any of the decoupling properties as such, right, in these simulations.
Not as such.
Okay.
No, can I come in here, Nishi?
Yeah.
So basically, that information goes in the transfer function, and in case you have hot dark matter or interacting dark matter, then the equations have to be different. And as such, this code is only geared towards dealing with the non-relativistic dark matter. If you have a relativistic component to dark matter, then you have to either solve Boltzmann equation, or you have to work with it with some other approximation scheme in order to emulate the large velocities and velocity dispersions that they have.
So, for example, for fuzzy dark matter, people will switch to Schrodinger-Poisson system rather than
Correct.
Yeah. Great, thank you.
So what I said is actually this suppressing this power at large scale. The reason is that even if you have something which is slightly warm or relativistic, by redshift 0, they will become, or when you start the simulation,
redshift 100 even.
Redshift 100, they would have become non-relativistic.
Correct. So if there is something relativistic, then you need a different prescription.
Right.
Non-relativistic, we can handle it. Doesn't matter what it is, it has to be non-relativistic.
It should be collision-less also. It should not. It should.
As long as it is collisions can be coded in, but not in this vanilla equations which were shown. Yeah.
So gadget is something which is heavily used. It's publicly available. Right now, there's a version called Gadget 4. The earlier versions were Gadget 2, which was public. Gadget 3 was not public. So if you are interested, you can download Gadget and see if you're able to run. If you face problems, again, we are there to help. I think the simulation which Asim has run was with Gadget 2, I suppose.
Yeah, that's right.
I have a question.
Yes.
So if we consider warm dark matter, so what will be the effect on the Halo mass function?
You will suppress things at smaller masses, right? So instead of it being a power law, there will be a truncation in that power law at lower masses. So you have a Schechter function. So that is just direct thing which I can probably say. So at lower masses, you will get a suppression of the counts of objects.
Okay.
In fact, the point is that because small scale fluctuations are completely wiped out, at small masses, you will simply not have any objects. So it is more than just suppression. It will be a truncation eventually. The mass function is disturbed. But I can also maybe show what if needed.
Okay.
And also I have another question. So for a given Halo mass, so if it provides some density, or we can get the estimate of this spherical over density. So by using this Brand-Norman empirical formula, so will that and this density will be at the time of formation, or it is the present density of the halo?
So what I showed is, if you want to look at the density in the current snapshot of the simulation. But if you want to look at the density in an earlier snapshot, you have to start tracking the set of particles that are there inside this radius and see whether you are able, they are coming from some another, from a region which is again identified as a halo. So that is how you will track back in time. So you need the particle IDs and you need to go back and
Maybe
see.
he's asking something slightly different. I can answer if you like.
Hmm.
So he's saying that this critical density that you showed, 200, is it to be applied at the current snapshot or at a previous snapshot? And the answer is, in typical ways in which you use the spherical collapse model, it is used at the time that you want to identify the halo. And there is a discussion in the literature about what is the correct time at which you should use such predictions. But this becomes then a matter of definition. So as long as you declare to everybody else what you are doing, things are fine. And in fact, this number 200 that that Nishi showed is also not completely agreed upon. So there are different conventions in the literature. So some people will take 200 times rho crit. Some people will take 200 times the background density. So then there's an additional omega matter. Some people will take what you were saying, this Brian and Norman fit, which will not be 200 rho crit, it will be like 100 rho crit, and so on and so forth. Okay, so every time you give a catalog of halos, it is your responsibility to tell us what is the mass definition that you used.
Oh,
So I will
okay.
show you some examples maybe of mass functions with different mass definitions in a bit.
And
So
this
if I
is,
want to,
just to interrupt again, sorry. So this mass definition is something which I think there is a lot of debate on. Okay, and because these counts, if you want to do cluster cosmology, now what is the mass definition that you have to come up with? So you have to worry about these definitions a bit seriously.
So when you're just talking about dark matter halos, it is a question of convention. You just say, this is the definition I use. But when it comes to observables, then you have to also be able to match your definition of mass to whatever it is that you are observing. So then it becomes a question of which definition tracks your observable most closely. So then there is a whole discussion in the literature about M500 crit being most closely attached to the X-ray luminosity of clusters, for example. Okay, so these kind of issues one has to then worry about.
okay, I see. So I just, if I have given a halo mass function and I want to estimate the virial radius of some halo, so we need to incorporate the critical over density or the density term. So I was using this Brian Norman density to get the.
That's okay. You can use that. So if somebody has given you the virial mass, then you can use the Brian Norman density to calculate a virial radius. That's correct. If somebody has given you M500 crit, then you should not use the Brian Norman density. You should use 500 times rho crit.
Right. Okay.
That is the. Since we are on mass functions, shall I just start my thing?
Yeah, yeah. So now Asim will take over. Yeah.
Okay, so I don't have much actually. So if we have enough time, I should be able to fill it. Let me share.
Stop my share.
Okay, desktop. So you can see my desktop, right? Not just a single window. Nishi, can you just confirm?
Yes, we can see your desktop.
Okay, take care. So I'll just go into this mode. So I just wanted to carry off from where Nishi stopped, and we have already seen such plots. So the purpose of these few slides is to just show you how to take a halo catalog from a simulation and produce these kind of functions. Okay, it is a very simple exercise. And I want to discuss a few conceptual things about these halo mass functions. So maybe just a recap of something that Nishi mentioned, which is the spherical collapse model. The idea of a halo physically is that there is a region somewhere in space where the density is so large that this region has decoupled from the expansion of the universe and it has become gravitationally self-bound. So this is the physical concept of a halo. And what Nishi described are empirical ways to go around in an n-body simulation and identify such regions in space. Okay, and the collection of n-body particles that constitute these regions, we will call halos. And now, once you have a collection of these halos, you want to ask what are the properties of such objects? How are their properties distributed? And the simplest property that one thinks about is the mass, which leads you to the mass function, which is just the number count as a function of mass, or the distribution function of the masses of these objects. So this is called the halo mass function. And what I'm showing you here is the halo mass function in the simulation catalog, which has been shared with you. I've forgotten what it's called. I think it's called hcat_mr, right? And then followed by some author name or something. So I will show you quickly how a simple way of analyzing this. But the solid line here is this mass function of halos in this catalog. And in the dashed and dotted, what I have done is to split up these objects into two kinds of objects. One is a parent halo and the other is subhalos of the parent halo. So I guess, Nishi, did you have a plot somewhere where you showed something like this? I've forgotten.
Pardon?
Did you have a plot somewhere where you were showing halos and subhalos? You did not.
No.
Okay, so how do I get it quickly? Can you share your screen and show from your presentation slides? There was this picture that Sandeep had made. No?
Yes.
Yeah, Shantanu, I see your question. So once the picture comes up, I will just explain.
So let me share. Okay, this is what you wanted.
The visual.
Sandeep. This one. Oh, the visual.
Okay.
I
just want to show visually what we're talking about. There was like a zoom in of a zoom in of a zoom in kind of thing.
This one, right?
Right now I can see baryonic effects, the galaxy stellar mass function.
Now?
Now I can see it. Okay. So for example, focus on the bottom right zoom. Okay, so what you see there are a bunch of filament-like objects, which are, and in the middle of these thick filaments, there are three filaments that you can see in like a lambda shape, dark colored. And then inside these filaments, there are embedded some very high density regions. Okay, so now if I look at the intersection of these filaments, this is almost certainly a gravitationally bound object. It's like a roughly circular region which forms the node of these three filaments. And that is most likely a big object. It is all the particles inside it are gravitationally self-bound. That is the working definition. But in that big circular region, almost like semicircular region, you see a bunch of very high density clumps. So those clumps are the substructure of this big region. So that big region is a halo. Okay, so it's like a large massive object. And inside that large massive object, there are other clumps where if you only focus on the particles of those clumps, you will again find that they are gravitationally self-bound to each other. And as a whole, they are bound to the gravitational potential of the larger object. Okay, so the larger object, I will call a parent halo. And these clumps which are sitting inside, which are also self-bound, I will call subhalos. This is the conceptual definition. Okay, so now I can go back to mine. You can stop sharing.
Yeah.
Okay. So what I did here is to just ask for the number counts of all objects, that is the solid line, and in the dashed and dotted, I have just split them into parent halos and sub halos. Let's just move quickly to the Jupyter notebook that I had shared. So I am assuming, let me assume that on average, people don't know how to use Jupyter notebooks. So I hope you have installed Jupyter notebook. And if you have, then it's very simple. You navigate to the folder on the terminal, or you can directly open it from Anaconda Navigator also. I will not do that here. And you type Jupyter notebook and the name of the notebook. So it's called this one. The other one I will also show you in a little bit, partially. Okay, so we'll just run this. And I hope you can see my browser. It opens in a browser. Okay. So the other thing you need for these kind of calculations is NumPy for doing the calculations and Matplotlib for visualization. And this GC is something which, if you're using Python 3, you will probably not need it. In Python 2, it's a way to keep your memory a little bit cleaned up. GC stands for garbage collector. Okay, so we will not really need it just now. But these first two lines you definitely need, because you need to calculate things and plot them. So I have just imported NumPy and I have imported Matplotlib. And okay, so just again, so if I add a new cell here, I have a choice between having a code cell in which I can say 1 + 1, and it will give me 2. Or I can say this is not a code cell, it is a markdown cell, in which case I can type things. So I can say this is a header and run this, and it will produce something like this. Okay, so this is just to show you how I made these headings, and it allows you to keep your notebooks clean and organized. Okay, so that's just cosmetics. This is the actual stuff. So what I need to first do is to load a Halo catalog. And I will just define a string variable called path. This part you can run it along with me, but you will have to change the string inside these quotes to whatever is your path of the place where you have put this Halo catalog. Okay, so that is the folder name. I have defined a variable called lbox, which has value 200 MPCH units. This is the box size of the simulation that we are using. Then these catalogs that have been given to you, hcat_mr something something, they have these author names, either Blanton or Dorta Prada, which will become clear in the next session when we do abundance matching. For the timing, you just pick one of them. And I have created a variable called infile, which is just a string which has the path, the directory, plus a string which gives me the name of the file. Okay, and I'm just asking the code to tell me what it's doing. Now, this thing is a list of tuples, and every tuple is organized as a string followed by a data type. So this is the way I will read my file. Okay, so my file has a bunch of columns, and the first column is an integer, and then all the other columns are floats. So what I want to do is to be